BSc Chemistry IR Spectra presented by Dr. Giridhar M, Assistant Professor of Chemistry, Department of Collegiate Education. In this section, we will be studying Introduction to IR Spectroscopy, the range of infrared radiation, vibrational spectra of diatomic molecules, so force constant, expression for vibrational energy and 0-point energy. So let us start with introduction to IR spectroscopy. So IR spectroscopy is one of the most powerful analytical technique which offers possibility of chemical identification of organic and inorganic structure. So from using IR spectroscopy, we can find the type of functional group which is present in the organic molecule, and in combination with other techniques such as NMR mass spectroscopy, we can use this technique to find the complete structure of molecule. The technique is based on simple fact that chemical substance shows selective absorption in the infrared region. After absorption of infrared radiation, the molecule vibrates at many rates of vibration, giving rise to close-packed absorption bands called IR absorption spectrum, which may extend over a wide wavelength range. So once we pass the IR radiation on molecule, the molecule shows selective absorption, and this selective absorption means here the absorption of radiation depends upon type of bonds which are present in the molecule, and therefore it gives an opportunity for structural identification of molecule. Various bands will be present in IR spectrum which corresponds to the characteristic functional group, the bond present in chemical substance. Thus, an IR spectrum of chemical substance is fingerprint for its identification. The molecule absorbs radiation only when natural frequency of vibration of bond in molecule is same as frequency of incident radiation. So that means natural frequency of vibration of bond should match that of the frequency of radiation which we are incidenting on the sample. Say for example, if our molecule contains OH peak, OH bond, OH frequency of vibration is around 3300 per centimeter, and when we are putting IR radiation on that molecule, it will absorb only radiation corresponding to its vibrational frequency, that is 3300 per centimeter. A molecule can only absorb radiation when its absorption changes in dipole moment. So this is one important condition for molecule to exhibit IR spectroscopy. That means the molecule must undergo change in dipole moment, okay, during absorption of radiation. So here homonuclear diatomic molecules are IR inactive because there is no change in dipole moment in these molecules. The dipole moment of oxygen, nitrogen and hydrogen are 0, and hence they are IR inactive. The range of infrared radiation. The infrared radiation refers broadly to that region of electromagnetic spectrum which lies between visible and microwave region. So that means in electromagnetic spectrum, the region of infrared occurs between microwave and visible region. And further, this infrared region can be divided into 4 sections. That first one we call it as photographic region. So this ranges from visible to 1.2 micrometer frequency. Very near infrared region, this is also known as overtone region and ranges from 1.2 to 2.5 micrometer. Near infrared region, this is also known as vibrational region and ranges from 2.5 to 25 micrometer. So it is in this region most of the functional groups vibrate. Hence it is also called as vibrational region. Far infrared region, this is known as rotation region and ranges from 25 to 400 micrometer. When analytical chemist speaks of infrared spectroscopy, he usually means the range from 2.5 to 25 micrometer or 4000 to 400 per centimeter in terms of wave number. Okay, so this is in terms of wave number, 400 to 4000 per centimeter. So this range gives the important information about the vibration of molecule and hence about the structure of molecule. The IR spectrum is a graph of transmittance or absorbance versus wave number. So in the IR spectrum, if you see on the x-axis we have wave number from 400 to 4000 per centimeter, and on y-axis absorbance will be there. Okay, absorbance 0 to 100. So vibrational spectra of diatomic molecule. Force constant. Force constant are the proportionality coefficients between the displacement of atoms from their equilibrium positions and force they induce on other atoms. So here we know that bonds are not static. Okay, the bonds are not static. They are like spring. So that means these bonds keep vibrating at their equilibrium position. They continuously keep vibrating, okay, along its internuclear axis, and that vibration is given in terms of frequency of vibration, which is nu, which is frequency of vibration. K is force constant, mu is reduced mass, and here frequency of vibration is directly proportional to square root of force constant, and it is inversely proportional to square root of reduced mass. So here force constant is nothing but the measure of strength of the bond. So if force constant is very much higher, the bond strength will be higher, and hence we require higher frequency of radiation, or the vibrational frequency of the bond will be higher. If the force constant will be lower, then the vibrational frequency of the bond will also be lower. So M is the reduced mass. Reduced mass is given by M1 into M2 divided by M1 and M2, where M1 and M2 are the masses of two bonded atoms. So therefore, in simple, we can say that force constant is the measure of strength of bond. Expression for vibrational energy. So here vibrational energy for diatomic molecule is obtained by solving the Schrödinger wave equation. So here on solving the Schrödinger wave equation, we get vibrational energy, which is E is equal to V plus 1 by 2 hc omega, where h is Planck's quantum number and V is vibrational quantum number. It can have values from 0, 1, 2, 3, and omega is vibrational frequency, and c is the speed of light. So this is the energy of vibrating diatomic molecule. So by substituting the values in vibrational energy, we get different values. So E nu is equal to 1 by 2 hc omega when V is equal to 0. When V is equal to 1, it is 3 by 2 hc omega. When V is equal to 2, it is 5 by 2 hc omega. So here we are substituting the value 0. When we substitute value 0, E0 is equal to 1 by 2 hc omega. When we substitute value 1, so it is 3 by 2 hc omega. So and by using Hooke's law, okay, when we plot this energy in Hooke's law, 1 by 2 kx square, which is the potential energy of that vibrating diatomic molecule, we get
different energy levels like this. This is E0, E1, E2, E3, E4. So like this. These are the vibrational different vibrational energy at different values of n. 0 point energy. 0 point energy is the vibrational energy that molecule retain even at the absolute zero temperature. So at absolute zero, it is not, the energy of the molecule is not zero. Instead, it is 1 by 2 Hc omega. So even at absolute zero, the molecule retains some amount of vibrational energy. Okay, so E energy is given by nu plus 1 by 2 Hc omega. When we put the value of nu 0, it will be 1 by 2 Hc omega, and this is called as 0 point energy. So even at absolute zero temperature, the molecule retains some amount of minimum energy, okay, and that is called as 0 point energy of the molecule. Transition. So when transition takes place, the electron will jump from V to V plus 1. So then it is given by delta E. The difference in energy is given by V plus 1 by 2 Hc omega minus V plus 1 by 2 Hc omega. So and here this cancels out. Okay, V 1 by 2 cancels out 1. So this will be only Hc omega. Okay, and delta E by Hc is equal to delta nu omega. So therefore, transition taking place from nu is equal to 0 to nu is equal to 1, the frequency obtained is called as fundamental frequency. Okay, this is called as fundamental frequency. So the only line obtained in the vibrational spectrum whose wave number is equal to equilibrium vibrational frequency of diatomic molecule. So this is called as fundamental frequency of vibration. Fundamental frequency of vibration. That is, so when electron jumps from this energy level to this energy level, it is called fundamental vibrational frequency. When electron jumps from here to here, it is called as fundamental vibrational frequency. If the electron jumps from n is equal to 0 to n is equal to 2, it will be twice the fundamental frequency, and it is called as overtone.
Selection rule and transitions. When molecule absorb IR radiation, transition occur from ground vibrational state to an excited vibrational state. For a molecule to be IR active, there must be change in dipole moment as a result of the vibration that occurs when IR radiation is absorbed. So the selection rules are given as delta nu is equal to plus or minus 1, so which is for fundamental vibration. Okay, delta nu is equal to plus or minus 1, this is for fundamental vibration, and when delta nu is equal to plus or minus 2, this is overtone, first overtone, and plus 3 it will become second overtone, so like that. And whereas for rotational, delta J is equal to 0 plus or minus 1, 0 comma plus or minus 1. So these are the selection rules for vibrational spectroscopy.
So these are the references. So thank you.